Monads in Leibniz philosophy and their potential connections to modern physics present a fascinating interplay between metaphysics and scientific concepts. Although Leibniz monads and the term monad in functional programming share a name, their philosophical grounding is distinct, with some abstract similarities. Here's an exploration of these monads in the context of Leibniz theory and their resonance with modern physics. Leibniz monads. Leibniz introduced the concept of monads in his metaphysical system to explain the fundamental nature of reality. Key characteristics of Leibnizian monads include indivisibility and simplicity. Monads are the basic, indivisible units of reality. They are simple substances without parts, akin to metaphysical atoms. Self-sufficiency. Monads are self-contained and do not interact causally with one another. Instead, their internal states unfold according to a pre-established harmony orchestrated by God. Perception and representation. Each monad reflects the entire universe from its unique perspective, akin to a microcosm of reality. This reflective property suggests a kind of holistic interconnection. Dynamic nature. Monads are not static, they constantly change, governed by an intrinsic principle of action or appetition. Connections to modern physics. While modern physics does not explicitly refer to monads, several ideas resonate with Leibniz' vision. 1. Quantum particles and indivisibility. Quantum mechanics. Elementary particles like quarks or leptons are indivisible in the sense that they cannot be broken down further, much like monads. However, unlike monads, these particles interact through physical forces, such as the electromagnetic or gravitational forces. 2. Non-locality and holism. Quantum entanglement. Entangled particles exhibit non-local correlations, suggesting a form of holistic behavior reminiscent of Leibniz' idea that each monad reflects the entire universe. While entanglement depends on physical interaction, it hints at a deeper interconnection underlying the fabric of reality. Holographic principle. In theoretical physics, the holographic principle suggests that the entire information of a system can be encoded on a lower dimensional boundary, aligning with Leibniz monads as microcosms of the whole. 3. Pre-established harmony and physical laws. Symmetry and conservation laws. The harmony Leibniz described might find a modern analogue in the elegant symmetry principles governing physical laws, such as Noether's theorem, which links symmetries to conservation laws. Noether's theorem is a profound result in physics that links symmetries in physical laws to conservation laws. Here are several examples of symmetries in physical laws and their associated conservation laws, demonstrating the elegance and harmony Leibniz might have envisioned. 1. Time translation symmetry conservation of energy. Symmetry. The laws of physics are invariant, do not change, over time. For instance, an experiment performed today will yield the same results as one performed tomorrow if all conditions are identical. Conservation law. This symmetry implies the conservation of energy. The total energy of a closed system remains constant over time. Example. A pendulum in an isolated system continues swinging with constant total mechanical energy, the sum of kinetic and potential energy, assuming no friction. 2. Space translation symmetry conservation of momentum. Symmetry. The laws of physics are invariant under spatial translations, meaning they are the same in all locations. A physical process in one place behaves identically in another. Conservation law. This symmetry implies the conservation of linear momentum. The total momentum of a closed system remains constant. Example. In a collision between two billiard balls, the total momentum before and after the collision is conserved, regardless of where the collision takes place. 3. Rotational symmetry conservation of angular momentum. Symmetry. The laws of physics are invariant under rotations. A system behaves the same regardless of its orientation in space. Conservation law. This symmetry leads to the conservation of angular momentum. The total angular momentum of a system remains constant in the absence of external torques. Example. A figure skater pulling in their arms while spinning rotates faster to conserve angular momentum. 4. Gauge symmetry in electrodynamics conservation of electric charge. Symmetry. Electromagnetic theory exhibits gauge symmetry, specifically the invariance under changes in the phase of the wave function of charged particles. Conservation law. This symmetry corresponds to the conservation of electric charge. The total charge in a closed system remains constant over time. Example. In a circuit, the total charge flowing into a node equals the total charge flowing out, consistent with charge conservation. Determinism and probabilism. Leibniz' deterministic pre-established harmony contrasts with the probabilistic nature of quantum mechanics. However, some interpretations, e.g., many worlds, preserve determinism at a universal level. 4. Emergence and consciousness. Integrated Information Theory, IIT. Monads' intrinsic perception aligns conceptually with modern theories of consciousness that explore how information is integrated and processed as a fundamental aspect of reality. Emergence in complex systems. Modern physics and systems theory examine how complex behaviors emerge from simple, interacting elements, paralleling the idea of monads dynamically representing the universe. Philosophical speculations. Relational ontology. Leibniz viewed reality as fundamentally relational. Monads relate to one another without direct interaction. In modern physics, relational interpretations of quantum mechanics, e.g., Carlo Rovelli's relational quantum mechanics, echo this idea, suggesting that quantum states are defined relative to observers. Discrete versus continuous. Leibniz monads suggest a discrete foundation for reality. Modern physics grapples with similar questions, such as whether spacetime is continuous or discrete, e.g., loop quantum gravity proposes discrete spacetime. Monads as information units. Some physicists and philosophers speculate that information is the most fundamental component of the universe, e.g., it from bit. Monads, as units reflecting universal information, fit this perspective. Conclusion. Leibniz monads, while metaphysical, offer a framework that intriguingly prefigures many modern ideas. They emphasize the indivisible and self-sufficient nature of fundamental entities, the interconnectedness and holistic representation of the universe, the role of dynamic change and perception in explaining reality. In modern physics, concepts like quantum entanglement, the holographic principle, and theories of emergence resonate with Leibniz monads, suggesting potential bridges between metaphysical and physical explanations of the universe. However, these connections remain speculative and largely metaphorical, rooted in the abstract similarities between Leibniz philosophy and the evolving paradigms of science.